Bismillahirrahmanirrahim. Sallallahu alayhi wa alihi wa sallam. Allahumma rabbi zidni ilma. Sallallahu alayhi wa alihi wa sallam. Ameen. Alhamdulillahi rabbil alameen. In this lecture, I will discuss the important concepts of rod and ring based problems with examples. And for this, I am using the work of an outstanding and one of my best student, Miss Sharika Batul of class 2020, the Lyceum. Case 1. This is the rod, this is the ring, and this is the tension in this ring. And this is the force diagram of this situation. See, this tension has two components, T sine theta and T cos theta. And this is the normal reaction force. Normal reaction always makes 90 with the rod. This is the weight of the ring. This is the frictional force because this ring is moving along the rod in this direction. So you just need to resolve forces in this way. T cos theta is greater than friction. And R is equal to W plus T sine theta because there is no motion perpendicular to this rod. So R is equal to, let me write the equations. Therefore, T cos theta is greater than frictional force. And vertical forces are balanced. So R is equal to W plus T sine theta because no motion perpendicular to rod. So with the help of these two equations, you can easily get the values of T and theta. Case 2. The rod is in vertical position. This is the rod, this is the ring, and this is the tension in this ring. And this is the force diagram of this situation. See, this T has two components, T sine theta, T cos theta. And this is the normal reaction force. Normal reaction always makes 90 with the rod. And normal reaction is the reaction of T cos theta. Since this ring is moving in downward direction along the rod, therefore friction will act in this direction, up the rod, because friction always acts against the motion. So you just need to use these equations. Horizontal forces are balanced. So R is equal to T cos theta. Since this ring is moving in downward direction, so W is greater than T sine theta and friction. So with the help of these two equations, you can easily get T and theta. This is greater than sum of these two. That is why this ring is moving in downward direction. Question number 20 and example number 1. This is the situation. This is similar to this case. Case 2. The diagram shows a ring of mass 2 kg threaded on a fixed rough horizontal rod, vertical rod, sorry. A light string is attached to the ring and is pulled upwards at an angle 30 degrees to the horizontal. The tension in this string is T newtons. The coefficient of friction is 0.24. Find the two values of T for which the ring is in limiting equilibrium. In this case, there are two possibilities. Maybe ring is moving in downward direction or maybe ring is moving in upward direction. That is why they ask find the two possible values of T. So you have to consider both the you just need to consider both the situations, like when ring is moving in upward direction, when ring is moving in downward direction, because in this case it depends. When rod is vertical and we have tension in this way, so these are two possibilities. Maybe ring is moving in downward direction, maybe ring is moving in upward direction. Well, this is the force diagram of this situation. This T has two components, T sine 30, T cos 30. This is the frictional force, and this is the normal reaction. Normal reaction makes 90 with the rod, and this is the reaction of T cos 30 degrees. We are considering first case. The first case is this. We are considering that ring is moving in this direction. And R will be T cos 30 because there is no motion perpendicular to rod. So let me correct this. This is R. So R is T cos 30. And we are considering that ring is moving in upward direction or about to move in upward direction. So T sin 30 is equal to friction plus 20. About to move means limiting equilibrium. So this is equal to sum of these two. So with the help of these two equations, we can get the values of T. We can get the value of T in fact. Now we will consider this thing. The ring is about to move in downward direction. You just need to change the direction of friction in that situation. You just need to write friction here. Case 2. When friction is in upward direction, meaning the ring is about to move in downward direction. R will be T cos 30 in both the situations. But in this, at this case or in this situation, 20 Newton will be greater than or will be T sin 30 and friction because friction is here. So friction will be in this direction. So T sin 30, this plus friction is equal to 20. Now with the help of these two equations, you can get the value of T. You can take this screenshot of this solution if you want. Case 3. This is the situation of case 3. This is the ring and this is the fixed point and this is the second ring. This is the weight of ring A and this is the weight of ring R. And these two tensions are equal. I mean, this triangle is isosceles. So the hint, how to solve this situation. You just need to resolve forces at this point first and then resolve forces at this point. Because we resolve forces at R first because maximum forces are acting at this point. At the next step, resolve forces at A. This system is in equilibrium, it will be given. Now see, when you will resolve forces at R, tensions will act away from R. Tensions will act in these directions, which is here. See, we are resolving forces at R, so tensions are acting in these two directions. So this tension has two components, T sin theta, if this angle is theta. If this is also theta, so this is also theta. So this situation is here. Weight of R, T sin theta, T sin theta, T cos theta, T cos theta. These two are balanced and sum of these two is equal to WR. So with the help of this equation, we can get the value of either T or W. I mean, if T is unknown, you can get T. If R is unknown, you can get R. Normally T is unknown. Step 2, resolve forces over here. This will become case 1. When you will resolve forces at A, you will get this situation. See, let me resolve forces over here. This is the normal reaction. The tension will act in this direction when you will resolve forces at A. So this tension has two components, T cos theta, T sin theta. This is the weight of the ring and this is the frictional force. So you will get this situation, which is here. Frictional force tension will act away from the point of resolving. This tension has two components, T cos theta, T sin theta. This is the weight of ring A and this is the normal reaction which makes 90 with the rod. So if the system is in equilibrium, then friction is equal to T cos theta and WA plus T sin theta is equal to R. This is the way to solve this situation. Take the screenshot of this concept because this concept is very important. Always remember that you need to resolve forces at this point first and then at this point. And these are the ways to resolve the forces. And this is an important question, exactly similar to that situation, case 3. A small smooth ring R of mass 0.6 kg is threaded on a light inextensible string of length 100 cm 50 each, means isosceles triangle. One end of this string is attached to a fixed point A. This is the fixed point. A small bead B of mass 0.4 kg is attached to the other end of the string and is threaded on a fixed horizontal rod. This is the fixed horizontal rod which passes through A. The system is in equilibrium, which is very important, with B at a distance of 80 cm. Number 1, find the tension in this string. For that, you need to resolve forces at R. And for that, you need to first get these angles. You need to drop a perpendicular from R to AB, get this angle first. Both angles will be same because of the isosceles triangle, and then resolve forces at R. So the angle is, in fact, the ratios of this angle are sin theta is this, cos theta is this, and tan theta is this. These ratios will be more helpful, instead of finding angle. So when you will resolve forces at R, you will get these things. This is tension, this is also tension. So this T has two components. See, we made axis at R. This is T, this is also T. So this situation is here. And this is the weight of ring R. So these two T sin thetas will be 6 newtons. So T is 5 newtons. This is the answer of part 1. Find the frictional and normal component forces at B. Now you need to resolve forces at B. This is similar to this situation. This will be normal reaction force. This will be frictional force. This will be, if this is T, then this will be T cos this angle, and this will be T sin this angle, and weight as well. So this resolving is here. Frictional force, weight of this ring, T is 5, so 5 sin theta, 5 cos theta, and this is the normal reaction which makes 90 degree with the rod. Now just need to equate these forces. 5 cos theta is equal to friction, and 5 sin theta plus 4 is equal to R. So this is the frictional force and this is the normal reaction force. Now the last part, we need coefficient of friction. You just need to use this formula. Friction is equal to mu R because the system is in limiting equilibrium. Whenever system is in limiting equilibrium, always use this formula. This is the coefficient of friction up to 3 significant figures. Take the screenshot of this solution because this solution, the question is very important. Case 4. Now we have this situation. So the hint is first resolve forces at this point and then resolve forces at this point. When you will resolve forces at C, you will have this situation. Make the axis at C. These are the axes. So F Newton is here. T2 has two components. If this angle is alpha, so this T2 has two components, T2 sin alpha, T2 cos alpha. If this angle is beta, so, or theta maybe, like in this case, so T1 cos theta and T1 sin theta. These angles are here. When you will make axis here, you will get these angles, alternate angles. This is alpha, whereas this is theta. Then you need to resolve forces at A. Here you need to just equate the horizontal components and vertical components. So this plus this is equal to F. This plus this, in fact, this is equal to this. Vertical balance, horizontal are also balanced. So by solving these two equations, you can get T1 and T2. Check this in here. This and this is equal to F, and these two are equal. This is also an important situation. Now step 2, resolve forces at A, at this point. So when you will resolve forces at this point, frictional, this is the normal reaction force. This ring is moving up the rod, so this is the frictional force, and this T1 will act in this direction, away from this point of resolving, which is here. See, this is the normal reaction force. This T1 has two components. This is T1 sine theta, whereas this one is T1 cos theta. This ring is about to move up the rod, therefore frictional force will act in this direction, downward direction, and this is the weight of ring A. Just need to equate these forces. This is equal to this, and sum of these two is equal to T1 cos theta. By solving these two equations, you can get the values of unknown. And the example question is here. A small ring of mass 0.2 kg is threaded on a fixed vertical rod. This ring. The end of A of a light inextensible string is attached to the ring. The other end C of this string is attached to a fixed point of the rod above A. A horizontal force of magnitude 8 Newton is applied to the point B of this string, where AB is 1.5 and BC is 2. And this angle is 90 degrees, so this is hypotenuse. The system is in equilibrium with the string taut and AB at right angle to BC in C diagram. Part 1. Find the tension in the part AB of this string and the tension in the part BC of the string. So you can suppose this as tension T1, T2. You can suppose this angle as theta. This is alpha, and you can easily get sine theta and cos theta. So this triangle is here. This is theta. This is alpha. So this triangle is here. So tan theta, sine theta, cos theta. All trigonometrical ratios are here. Now you just need to resolve forces at B first. So when you will resolve forces at B, you will get this situation. This is B. 8 Newton force is here. This is T2. You can suppose this as T2. This is T1 with angles theta and alpha. And because of alternate angles, this will become alpha. Alternate angles properties, this will be alpha and this will be theta. So this T1 has two components. This is T1 sine theta, whereas this one is T1 cos theta. T2 sine alpha and T2 cos alpha. You just need to equate this and this with 8 newtons. And this is equal to this. So with the help of these two equations, you can easily get the values of T1 and T2. This equation and this equation. This is tension in AB and this is tension in BC. This is T1 and this is T2. The equilibrium is limiting with the ring on the point of sliding up the rod. Find the coefficient of friction. Now you need to resolve forces at A. when you will resolve forces at A, T1 will act in away from A in this direction, which is here. C, T1 will act in this direction. Normal reaction force is here because it makes 90 with the rod. Since this ring is about to move up the rod, therefore friction will act down the rod in this direction. This is the weight of ring A. This angle is theta. You have option. You can directly resolve this, or you can use 90 minus theta. This is your choice. If you will resolve this directly, then you just need to write 6.4 sine theta, and this is 6.4 cos theta. It's your choice. This student use this angle. It's optional. Now just need to equate the forces. R is equal to this, and this is equal to sum of these two, and get the value of R and F, and use this formula. Friction is equal to mu R for mu, and this is the answer of mu. Now take this screenshot of this solution, because this question is also very important. Another example of case 4. A small ring R is attached to one end of light inextensible string of length 70 centimeter. The total length is 70. This is 40 and this is 30. Total is 70. A fixed rough vertical wire passes through the ring. This is the vertical wire. The other end of this string is attached to a point A on the wire. A horizontal force of magnitude 5.6 Newton is applied to the point J of this string 30 centimeter from A and 40 centimeter from R. The system is in equilibrium. Of the parts AJ and JR of this string taut. Find the tension in the part AJ and tension in the part JR. We need these two tensions. So let's suppose this angle is theta and this angle is alpha. So with the property of alternate angles, this will be theta and this will be alpha. You can suppose this as T1 and this as T2. And this triangle is right angle. So first you need to resolve forces at J and get the values of sine alpha, cos alpha, and sine theta and cos theta with the help of this triangle. Now, when you will resolve forces at J, then tensions will act away from J. So this T1 has two components, T1 cos alpha, T1 sine alpha. This T2 has two components, T2 sine theta, T2 cos theta. So you just need to equate these two with 5.6 and T1 cos alpha with T2 cos theta. And by solving these two equations, you can get the values of T1 and T2. The most important thing is the correct force diagram. Here are the values of T1 and T2, T2 and T1. Now the next part. The ring R has mass 0.2 and is in limiting equilibrium on the point of moving up the wire. So friction will act in the downward direction. Show that the coefficient of friction is this. So you need to resolve forces at R now. When you will resolve forces at R, then C, friction will act in this direction. Normal reaction will act in this direction because it makes 90 degree with the rod. And this tension, this is T2. This tension is T2. So this T2 has two components. This T2 has two components. This is T2 sine theta and this is T2 cos theta. So you need to equate R with this and this T cos theta with sum of these two. So 3.36, T2 is 3.36, sine theta is equal to R. This is sine theta. Let me edit this. So R is 2.016 newtons. Now you need to equate these two with 3.36 cos theta. So friction will be, and we will use the formula of friction, which is mu R here. So mu is this shown. Now the next part, a particle of mass m kg, another particle, a new particle of mass m kg is attached to the ring R, and R is now in limiting equilibrium and a point of moving down the wire. Therefore friction will act in this direction. Given that the coefficient of friction is unchanged, find m. This is so simple. See, the weight of this new system, the weight of these two particles will be m plus 10. So it will be 2 plus 10m. This is the weight of these two rings, and friction will act in this direction. So, and this is about to slip down, these two rings. So this will be friction plus 2.688, meaning friction plus this is equal to 2 plus 10m, and R is equal to this. So with the help of these two equations, you can easily get the value of m. This question is very important. Please take the screenshot of this solution. If you need this file, then you should WhatsApp me to get this file. You just need to WhatsApp me. Take my number from the banner of YouTube. Next example. This is the ring R. A small smooth ring R of weight 8.5 newtons is threaded on a light inextensible string. The ends of these strings are attached to fixed points A and B. Because of the alternate angles property, this angle will be theta and this will be theta, and this will be 90 minus theta. So the ends of the strings are attached to fixed points A and B with A vertically above B. A horizontal force of 15.5 newtons act on R so that the ring is in equilibrium with angle ARB 90 degree. The part AR of this string makes an angle theta with the horizontal, and the part BR makes an angle theta with the vertical. See the diagram. The tension in this string is T Newton. The tension is T. Show that T sine theta is 12 and T cos theta is this. This is simple. We just need to resolve forces at R. So 15.5 is here. This is the tension T. This angle is theta. You have option. You can either use this angle or this 90 minus theta. So this T has two components, T sine theta, T cos theta. This is T sine 90 minus theta, which will become T cos theta, and this will become T sine theta. and this is the weight of the ring. We just need to equate the horizontal components and vertical components. So horizontal components first. So t cos theta plus t cos 90 minus theta is equal to 15.5, which is here, and this is equal to this plus this. By solving these two equations, you can get the values of you can first prove these two equations and then you can get the value of theta. For theta, you just need to divide these two equations. T sine theta, t cos theta, 12 upon 3.5. T will be cancelled. This will become tan theta, and that's the answer. Another question of this type. This is the last question of this lecture. A smooth ring R of mass 0.16 kg is threaded on a light inextensible string. The ends of these strings are attached to fixed points A and B. The ring is in equilibrium. The string is taut. The tension in this string is T. So this angle is with the help of alternate angles property, this is theta, and this will be 90 minus theta. Tension, tension. Now you just need to resolve forces at R. So this T is here with angle theta. So it has two components, T sine theta and this, and the other T has two components. Let me edit this. This T has two components, T sine 90 minus T cos 90 minus theta. And this is the weight of the ring, which is I think 1.6 newtons. Now you just need to equate horizontal and vertical components. So this plus this is equal to 11.2, and T sine theta is equal to this plus this. With the help of these two equations, you can get the values of T and theta. T is 8 and theta is 53.1. Well, this is all. Alhamdulillah, we have done rod, ring and rod based problems. Good luck to everyone, and I am extremely thankful to Ms. Sharika Batul who helped me to make this lecture. Indeed, she is an outstanding student. May Allah Pak bless her always. Ameen. May Allah Pak give her the best grades in all her exams.